Okay, and good afternoon, everyone. I'm Mahtab Mirmohseni, a senior lecturer at Institute for Communication Systems, University of Surrey, and I will talk about silent target localization using molecular diffusion. And this is a joint work with Ladan Khalupur and Professor Nasiri Kenari from Sharif University of Technology. Molecular communication is a new communication paradigm that uses molecules as information carriers. And besides this traditional message transmission purpose, it's proposed for abnormality detection and localization applications, both in micro and macro scales. In micro scales, mostly for in-body applications, for healthcare monitoring and targeted drug delivery systems, and also in macro scale applications for detecting and localizing the abnormality in pipeline, both for industrial and environmental applications like quality of monitoring of tap water and search and rescue services. The target localization works in molecular communication and can be categorized into three main categories based on the target type. The target can be either a source of molecules that releases molecules, it can be an absorbing node of molecules, or it can be a silent target. And that's the focus of this work, and I will describe it later. In the first two scenarios, the target changes the concentration of the molecules in the environment, and we have a receiver that tries to detect that change, and based on the measured change, it decides the location of the target. But in the silent target case, the target either does not release any molecule and just changes another environmental parameter, such as temperature, pH level, or it releases molecule, but the concentration of molecule is very low and it cannot be received by another receiver in a distance. And so we also have another assumption here, because in most application, the physical access to the abnormality point is infeasible. So we use mobile sensors to move and reach the abnormality point and send sensory data from the vicinity of that target. So we consider this case the silent target case, and we wish to use mobile sensors. All these three types of targets are studied already in the literature. For type 1, there are works that consider one receiver or two receiver or three receiver in the three-dimensional case to find the location of a point source of molecules. Also, for type 2, there are works that consider some type of receivers that try to detect the absorbing nodes and also to localize it. For silent target, there are works in both micro scale and in macro scale. Here we concentrate on the work on micro scale, because in macro scale, the scenario somehow changes because we need some flow in the medium to be able to receive the data. But here we focus on micro scale scenario. The existing works use mobile sensors to detect or find the abnormality, and they help each other to find the location of the abnormality and track that abnormality. So the sensory data is not sent to another node to be able to decide there. Here, we wish to consider a system where the mobile sensors move and find the abnormality and send their sensory data using some molecular communication setup to localize the abnormality. Here, again, we do not use molecular communication just for message transmission because these sensors are not very sophisticated nanomachines. There are very simple sensors and they can just release molecules when they get activated. So the sensing and communication is somehow integrated in this molecular communication setup. For this, we propose this system model. We consider a bounded two-dimensional area where the abnormality is uniformly distributed, and we assume that it's already detected, and our goal is to localize the abnormality. We have three types of devices, some mobile sensors, 2 or 3 fusion centers, and a gateway. And our localization process has 4 main phases. At the phase 1, some sensors are released into the area and they move randomly. And if they reach the abnormality point, they get activated. And they sense the change of that environmental parameter and they get activated in the abnormality point. In phase 2, the active sensors release molecules at the abnormality point. They can do it collaboratively or non-collaboratively, that I will discuss later. And the released molecules diffused in the medium and some of them will reach the fusion centers. At phase 3, fusion centers receive the molecules, amplify them, and forward them to the gateway using some markers. And finally, at phase 4, the gateway, after receiving the markers, decides on the location of the abnormality itself, or the signal can be converted to an electromagnetic wave and be transmitted to an external device. We want to simplify the problem, so we assume that the gateway itself decides the problem. So our focus is on phase 2 and 3, where molecules are released by the sensors toward the fusion centers, and also fusion centers send it to the gateway. At first, we assume that we focus on phase 2, and we assume that the channel from fusion center to the gateway is an ideal channel, and then we extend the result to the noisy channel. We derive the decision rules, probability of error. We consider 2 types of sensors. First is the collaborative sensors. Here I emphasize that this collaboration is just to transmit the data of the location of the abnormality to the fusion centers. This means that they collaboratively release molecules. For the collaborative sensors, they use some quorum sensing type of collaboration, and if their the number of the activated sensors reaches a certain threshold, they start releasing the molecules. But the non-collaborative sensors, we assume that they have limited energy storage, and after some pre-specified time, the active sensors release the molecules. So for these 2 cases, we have first we have the ideal channel and then the noisy channel. For the ideal channel between the fusion center and the gateway, I will describe the system for the collaborative sensors. Here, the number of the releasing molecules is deterministic. It's equal to that threshold that I mentioned. But the time of releasing molecules is a random variable. So in this case, 2 fusion center is enough to find the location of the abnormality because each fusion centers start sampling after releasing the sensors to the medium. And when it receives some positive amount of molecules, the fusion center knows that this is the correct time slot, and of course we find the observation time that the fusion center must wait. I will describe in the next slide, but so we don't have anything random here, and the fusion center can estimate its distance to the abnormality point based on the molecules received from the sensors. And having two distances, we cluster the area based on these two distances with some resolution, and we find the cluster of the abnormality. I don't know if I think now you can see. Sorry for this. And here it is how we cluster the area based on the resolution on D1 and D2. So since the number of the sensors is deterministic, here two fusion centers is enough. For decision rule, each fusion center uses k observations, and since the mean and the variance of the observations, which is a binomial random variable, depends on distance, it can decide on its distance from the target. We use Gaussian approximation for this binomial random variable. There is a challenge. We don't know what is the peak time because the peak time depends on distance. Here we use an approximation and we assume that the abnormality locates at the center just to set this sampling time. We use maximum likelihood decision for the distances, and also by comparing to adjacent clusters, we derive simpler suboptimal threshold-based rules. And also for the probability of error, we showed that the error event random variable has non-central chi-square distribution, so it's easy to find the probability of error. And but for the non-collaborative sensors, where they have some limited storage for energy, and after some specific pre-specified time, which is shown by this TTH, the active sensors start releasing molecules. In this case, the number of the active sensors is a random variable, and this is a challenge because the observation at each fusion center now is a doubly stochastic random variable, and their mean and variance depends on NR. So we cannot use this observation to determine the distance. To tackle this challenge, we use 3 fusion centers, and we estimate Sx using the observation from FC1 and FC2, and Sy from observation of FC2 and FC3. By this, we consider the ratio of the fusion centers observations, and we eliminate NR from the mean of the observations. Also here, because we want to find Sx and Sy, we have the clustering is different from the previous case. I don't want to go into the details, but considering the ratio of the observation, now we can estimate the distance. We also use another technique because the variance still depends on distance. We use minimizer of the mean square error to find the variance of this random variable. And after that, we use maximum likelihood decision. And we can find the probability of error. To consider phase 3, now we have instead of fusion center observation, we have the gateway observation, which is the doubly stochastic random variable, which it means depend on YIK. So it's not easy to find the distance from this random variable. We use mean value approximation technique, and then we extend our previous results. Here you see the probability of error for our two cases, collaborative and non-collaborative sensors. In the left figure, it's shown the probability of error is shown versus the total number of the released molecules. And you see that as the number of the molecules increase, the non-collaborative scheme outperforms the collaborative one. Also, this show we have the simulation results, and we see that for the collaborative case, the simulation results perfectly match the numerical ones. But for non-collaborative, there is a slight gap because of those approximations that I mentioned, the mean value approximation. And here this effect is shown better because we see that when we increase the number of released molecules in the lower curves, the non-collaborative sensors outperform the collaborative one, and in particular in the mid-range resolution. Also, I forgot to mention that to have a fair comparison between two cases, we set the number of the active sensors equal in two cases. If we consider the effect of the noisy channel, we see that by increasing,
your time is running up. If you can go faster to the conclusion.
Yeah, this is the last slide. And okay, here I skipped the noisy case, and I just want to show that the simulation results confirm the approximation that we made, that mean value approximation. And to conclude, we propose the molecular communication setup for a silent abnormality localization case. And we did it using three types of devices: mobile sensors, fusion centers, and the gateway, and analyze it for collaborative and non-collaborative sensor case. It's observed that non-collaborative sensors outperform the collaborative one by increasing the number of the molecules, and also the proposed model can be easily extended to the three-dimensional environment by adding one more fusion center. Okay, if there is any question, I will be happy to answer.
Thank you very much. Is there any question? No, may I ask a quick question? As I well understood, in your model does not react, right? Could you include some reaction activity of this molecule? Because once you have a molecule, always tend to react. So the concentration of the molecule could give you some information of what's the time that the molecule spend traveling, if you like. Could you include this something like that?
Yes, thank you for the question. Yeah, actually, it's possible. It's a good idea at least to consider some reaction type of sensing for the mobile sensors. Because in this work, we consider that we actually ignored that part of the sensing, and we assume that when molecules arrive in the vicinity of the target, they will be activated. But if we consider more detailed system where the molecule activation depends on some reaction between the targets, for example, release markers, and the molecules, for example, receptors, this will help. Also, if we want to consider the reaction between the release molecules of the by sensors, I think you mean this, Okay, that in that case we have to solve that reaction diffusion type of equations, and that I think in this case they do not have a general solution, but with some assumptions, I think it's doable.
I was thinking about the molecule reacting in the medium where they actually diffuse, not with the other interface. During the travel, they can diffuse, they can react and transform in another molecule. So the concentration of the molecule, it depends on how many time they spend on the medium.
Yes.
So you can get some information from the concentration profile.
Yeah. In that, we need to solve more complicated reaction diffusion equation in that case, by considering other type of maybe molecules that react with this one. So yeah, it's doable, but I'm not sure if there is any closed form solution for that.
Okay, thank you. Any other question? No. If not, we can thank again. Ali?
Thank you.